compression. And Gauthier de Montmorin from Switzerland is here to explain how he did all that in Ada.
Exactly. Yeah, thanks. Hello, everybody. So this presentation will be hopefully not too painful hour about lossless data compression in Ada. Or I could not resist to put a buzzword variant of the title, enhance your data-centric compression to the extreme maximum by leveraging machine learning. Okay, actually, there is some kind of primitive machine learning, so it's not all bluff, the title there. And the second part will be about more broader about the zip Ada library. So it's about zip archive and compression. Now we begin with a small experiment. First we take a text and we compress it, so you have a bunch of random bits shown with pixels. And then you concatenate text 1 and text 2, and you have a bit larger bunch of bits. And the third one is only text 2 compressed. And as you see, and as you have guessed, the compression of the part above text 1 is better than the text 2 alone, because the algorithm has learned something from text 1. Of course, text 2 is similar to text 1. It's why it works. Otherwise, it would be the other way around. Let's see better with some animation. So I swap between A and B, so text 1 and text 1 with 2 concatenated, and you see this part is identical. Okay, you will have spotted a few bits, but it's not, it's part of a header. It's before the compressed stream. So it indicates that this part will contain the compressed version of text 2. And the interesting thing, it is much smaller than just compressing text 2 alone, with just without prior knowledge. So the conclusion is, like with sports and other things, compression is better with a little training. So as I see it, perhaps there are more ways, but I see basically two ways of doing that. Either you compress, say, the text 1, and you save everything from the compression algorithm. The dictionary, the probability model, and the state of the finite state machine, basically. So you save all that. Actually, it can be a very large bunch of data, this information, much larger than the things to be compressed. Or you use prefix data. So you do actually exactly like in the experiment. You feed the algorithm with text 1, but actually you won't use it in live. It's just for training the compression algorithm. And then the text 2 is what you want to compress. The advantage of the lazy way, so the way 2, is that you can just reuse a normal compression algorithm. You can leverage it as is. So what I've done is I've made a package that you can plug onto a compression algorithm, and it does the job. You don't have boring API or very complex data structures or for saving things from the variant 1 and stuff like that. There is one disadvantage, of course, when you run the compression side, it takes longer because you have to compress what was text 1 in the experiment, and it can be time consuming, but sometimes you don't mind. You are more interested in decompression often. So where to use this trained compression? For instance, you anticipate having large amount of data that are all similar together to some extent. Of course, they are not the same. So you can have a sample you use as a training data, and then you have thousands of different files. You don't know them in advance, so perhaps it's from something over the internet, and you will always use the trainer file first for training the algorithm. And as with the experiment, you will save storage. So perhaps if you have millions of this text too, it can be large storage, or you can save transmission time. I kind of know an application on this side of the room. And perhaps there are other advantages that can be found, but it's what I've found by developing that. So how it works a bit graphically. So here you have the compression side, and here you have the decompression side. So basically, first you put your training data, so the text 1, into the compression engine, and then your data. And what will happen, I need to say it must be a streaming compression algorithm. So nothing that mixes the order of the stream, otherwise it won't work. But if it is a streaming like LZMA or deflate and LZ-based algorithm, for instance, you will have first the compressed training stream. You discard it, you don't need it. But now the algorithm is trained. The probability model is trained, and the dictionary is full with nice words from text 1. And then comes data 2, and here you have a big wall or hurdle, and you need to send it over. It's slow or expensive or whatever. It's over the internet, I don't know, but you want to have a better compression for that. So you have your compressed data shipped there. What happens on decompression side? First, you stuff the compressed training stream, but of course, this one was not shipped over the big hurdle. It was already known to the computer on the decompression side. So it's shipped only once in the life of this machine. So you put first the training data, and then the compressed data, which was of course unknown to the decompressor. And what happens, as you guess, you have the training decompressed, you discard it, you don't need it, and you get your data decompressed as you wanted. So here is the ADA specification of this train compression. So I didn't do any fancy object-oriented thing. It's only with generics. So you don't have. It's very simple. You have only a function which give bytes and a function procedure which writes bytes in each time. But the difference to similar things, you have two inputs. You have the training input and the data input. On the decompression side, you also have two inputs, one for the compressed training and one for the compressed data. Because you need two functions, because one is will take locally from the local computer, basically, and the second one will receive from the big antenna the interesting data. And then you have, once you have provided these functions and procedures to have inputs and outputs, you have on encoding side encode, and it does the job. And you have also decode on the other side. So you were certainly impatient to see some results. So I begin with perhaps with data where it's not too impressive. So I have CSV files. It's things that economic data that you can download on the internet. So it's all public. It's also all on the SourceForge and repository and GitHub Mirror if you want to test it yourself. Yeah, with CSV files, basically you have random data, but a very restricted alphabet. You have figures and commas and end of lines. So there is nothing that the training can bring actually, not a lot at least. Here you have, on the left side, you have Excel files, the binary, the old binary format with plenty of metadata. And then you see it's much more efficient because all this metadata is present in all Excel files. So the training brings a lot. So perhaps in the last 8 or 5%, you have really squeezed the real information in these Excel files. And in the middle, I've just compressed the encoder using the decoder as a training file. Of course, they are similar because you have the GNAT runtime and perhaps the debugging symbols and things like that. And you get a lot better compression by training the algorithm. So here it's a Windows executable, so it could be different with different formats. But it's almost 1/4 of what you would get with LZMA, which is a very good algorithm. Now, second part is more about the zip ADA library. So what is it? It's okay. We are at the right place here. It's fully open source, and we are in the right dev room. So it's fully in ADA. You don't need to even think about interfacing the stuff. Usually it's the painful part of using mixing languages. And it's fully portable as long as you have a compiler supporting the certain number of integer types, of course. So you need a complete Ada compiler with the necessary integer types. So portability, you have just one set of sources. You don't have magic with conditionals and if-def and these kind of things you use. Especially in compression software, usually you see kilometers of if-def, define, include, blah, blah. So that's not there. So more details about portability. So again, there is no binding. It's standalone. It uses Ada streams and exceptions. You can monitor, control, analyze your program, including the compression library with the same tool set. And on the right-hand side, here a list of platforms that where zip and Ada has been is in use or has been in use or for some time. So I didn't check personally all the platforms, but I trust people sending me mails about it. If you have another platform, please drop me a line, because the bigger the list, the better. The history of zip Ada, so it's 20 years old soon. So first it was a bit ugly translation. It was only decompression. It was a translation of Pascal with some, yeah, it was not so nice. And over the years, yeah, I had a good idea, or someone perhaps told me or recommended me to put it on an open source platform. At the time, SourceForge was the number one or whatever. So in 2007, I've put it on SourceForge. And then the magic of open source began, because people began to use it. And soon after, I got a nice contribution in 2008. So basically, this team in this company did a big chunk of the zip Ada library, and they sent me per email. So there they have programmed the streams. Before it was only files, and they did the zip archive creation site. And it's nice because they did it very orthogonally, because you can have a zip archive in a stream. You can have everything in memory. That's fantastic. Or whatever medium you want. You don't need files. So you can have your almost kind of RAM disk or static RAM disk using a zip archive with a file system and everything. And then I got other contributions, and I developed, I have added some decompression things. And later I've added, okay, I have bite the bullet, I've added a LZMA decompression. That was not so easy, but fortunately it was due to the fact that there was finally a well-written C++ simplified reference decoder for LZMA by the author of LZMA. So I jumped on the wagon and I've translated it into Ada. And then I wanted to do a bit more and have a strong compression. So I began with deflate. And then it was in early 2016, then during the vacation of 2016, I did the LZMA compression. Actually, it was easier than anticipated because you can mirror many things from the decoder. You can just swap the bit inputs into outputs. And now what I've presented just earlier, the trained compression. So how does it compare to other methods and so on? There are plenty of libraries. You have this, if you check this squeeze chart site, it's done by an expert of compression. He has hundreds of different schemes and he lists only those that are working. and yeah, the problem with compression, the definition of a good compression, it's a bit shaky because some people just want to have a good compression ratio. But sometimes if it takes too long to decompress, it's no more interesting because you have good capacity networks and so on. So it's also important to have a good decompression time, or sometimes not. But if it takes really too long to compress the data, it can be also a problem, or perhaps not, because sometimes you have something you compress once and it's downloaded thousands of times, so you can care or not about compression time. And finally, that's more about the embedded systems. You have the question of memory footprint. You want to keep all the internal tables of the compression and decompression within a certain constraints. So here you have a picture with two of these criteria. So you have the compression ratio. So on the smaller, the better. And here you have on the logarithmic scale, the time of compression. So as you guess, the more you go to the frontier of compression, the longer it takes, tendenциally. So the zip-ada library is not the all best on this part, but perhaps, who knows, in a few years, with some effort and whatever. So a little bit about the internals. So deflate and LZMA, so the things I have implemented relatively recently, they are both two stages, two phases algorithms. So you have first a string matcher, so the LZ77 algorithm. And then you have the entropy encoder to squeeze this pre-processed signal, basically. And it's the same principle for deflate and LZMA, but with deflate you have Huffman trees. LZMA, it's range encoding. It's a much more powerful compression scheme for entropy. So now, how you again a comparison only with the zip format. So here it's a kind of standard benchmark data set, Silesia corpus. So here you have the 7-zip, and here it's InfoZip, so the same as zlib, bzip2, and again 7-zip, but with the LZMA compression. And here in green, it's the results with zip ADA. So it's not too bad. And one good thing of the fact that it's in two phases, you can pick and choose the algorithm, the string matcher, so the LZ77 part, and see how it works with the entropy coding. Sometimes you have surprises. So for instance, I've picked for LZMA something that was for deflate, and it works pretty well. And also for certain kind of data, I've discovered it's better not to compress with the first phase. Just send the plain bytes. It compresses better than with a string matcher. So finally, another, let's say, innovation in the zip ADA library. You have a kind of meta method that leverage or that correspond to the fact that in the zip file, each entry, so each file in the archive, is compressed individually. So you can pick and choose the algorithm for compressing it, depending on the length, for instance, or the type of data. Especially the length, I've noticed that the files that are shorter than more or less 9 kilobytes, they compress poorly with LZMA. And if you see the probability, all the tables for the probability model, you understand it needs a long stream to train the algorithm. So an individual file shorter than 9,000, you can just forget LZMA, you take deflate, and it's better. So that's for the presentation, that's it. I'll make a little demo, perhaps. It will be, perhaps it's interesting, hopefully. So here you see a zip file. Okay, it's a spoiler for the next presentation, but I just show you the contents with a user interface. In the meantime, okay, the user interface is, so you see a bit the contents. Okay. Some text, I've put some text, some XML files, database, and we'll see what happens with different schemes. So, So I'm just unpacking the thing with the command line version, which is shipped as a demo with the library on SourceForge. And what can I do? Okay, I can show you. When something is decompressed, you also have a hash code checking to be sure. So everything is fine, and of course you can use the compressed file. So there's no magic. So, for instance, I open this file, and you see the the charts that were before, and so on and so on. And now, if I for instance, so I recompress with the fastest deflate, so basically the default scheme. So you have a new archive as expected. So now, let's say I'm paranoid, I'm not, what is this zip ADA library? So there is a tool called compzip, which compares every contents of zip file, but byte by byte, not only the hash codes. So it's checking, so it opens every entry of both archive. Everything fine. Oof. Now I'm just showing the options of. So you have different compression schemes, and what I've just shown, the latest, this preselection method, so meta method for doing pick and choose. So let's see. So for instance, the PDF files, it chooses LZMA with certain parameters. So you have 225 different ways of configuring LZMA, for instance. And so you have different sets for different data types. So as you see, the latest compression, so with preselection, is hopefully smaller than the one with deflate. And what can we do? Yeah, I think it's it for the demo. I have some further slides, but I don't want to. It's a bit technical, and so I think I will stop. I will stop the presentation here. But I'm sure there are plenty of questions. Oh.
Well, I actually do have a technical question here that's concerning the trainable part of your algorithm. So judging by the timeline, it was added like within the last year. I would suppose nowadays people would use recurrent neural networks. That would be the first thing that springs to mind. Then you ship like the training, the topology plus training parameters to the other set and use complementary generative neural network to reconstruct the data. Is this the approach, or?
No. The approach is just it's very simple. Just feeding data to the same It's very lazy. It's I just put into the compressor.
So you just tune some of the parameters of the compressor. What is the pre-training in this case?
All compressors begin with a neutral state.
So you basically just train to shift the parameters.
Exactly,
Optimize for
exactly,
specific
exactly.
settings. Just, you change
And
the
it seems I'm very lazy. Instead of
so
saving,
your topology is fixed then, in other words. Okay, I see.
but probably there are smarter ways, or using you could use yeah.
Just as I described, this one should be able to beat. I mean, domain-specific data compression would, of course, beat generic data compression, and it really depends on domain. You can get up to 99.99 in some cases.
Of course,
it really depends on the domain. So that's why I was asking about approach. But since this is text, like textual data we are talking about, that's why I suggested RNNs.
It was only for the experiment, but you can put binary you can put everything.
Depending on the nature of data, you would use different constructs.
Yeah, but as the chart with the comparison, you had Excel files, so I've trained
That would be
with an Excel file for compressing an Excel file, and an executable was used for compressing an executable for the same machine, and so on. Of course, you leverage all as a human, when you put the training data, you know, or you guess it will be similar.
The best compressor kind of builds the model of the data, but then since you are operating with standard algorithms, your models are fixed. But okay, I better let others ask. We have questions. So yeah, thank you.
So is the training only for LZMA?
No, I've tested with LZMA because it's the most powerful in the toolbox. But well, for instance, with something like bzip2, which is a block sorting algorithm, it's clear it won't work because everything is sorted in huge blocks. So
the training only applies to certain compression algorithms.
Yeah, which are streaming compliant, if you want. So the output stream is in the same order than the input stream, except it is squeezed, it's smaller.
And again, with the training, you surprised me with what you've shown, because that's not what I thought you were going to do.
It was the ambition.
The idea of the training was that you could train it on itself. So before you send it, you train it on itself by basically reading, although it's a stream.
Yeah.
The file in twice, and therefore.
Yeah, but then you would have the perfect compression.
No,
you would have one.
Instead of it building up or learning, you said LZMA is adaptive. So as you get through whatever stream you're getting better and better.
Yeah.
So by the time you come to the end, you really know this file really well. You then threw away the data. Instead of transmitting it or doing whatever you want to do with it, if you then started processing the same file again, you would be...
You would have... You would have just...
Compress it because you're missing the information on the other side.
This competition, if I got the name, where basically the idea is you are given a huge file, text normally, and you are supposed to produce the best ever possible compressor, but the trick is you have to include the compressor itself in the size estimate, because you could of course just simply data and write the one like...
I guess you wanted to refeed or you restart
here again,
the compression. Yeah, but I can tell you what will happen, because the dictionary probably you have set it as long as possible to perhaps contain the full decoded stuff. The compression, the string matcher will notice that you just put the same, so it will send a big, just a single distance length code, just the length of the or your uncompressed thing, and with the distance as well. That's it. Just one code, or perhaps a chunk. If the lengths are limited, a string of lengths. But
back references that mean nothing if you have nothing.
yeah, it won't help if you want to send to machine B. Machine B doesn't know of your string. Yeah.
What you're sending over to machine B is a mixture of this dictionary and...
So I show you again the scheme. So I have two instances. It's too much. Stop. Okay, so what you need to send is this data in all caps. So
data dash is what's...
yes, yeah.
Data dash is a mixture of the real data and some sort of dictionary or something like that.
Not at all.
It's
the
to decompress it.
data slash is just the compressed version of data.
Yes.
Full point.
So that's all you need to decompress it.
Yeah.
Right.
Yeah.
And that wouldn't be better. And data dash is generally is a result of data.
Absolutely.
Right.
Yeah.
And you say you start off at it's all at the zero state when you started. So it doesn't know anything about the data that you're going to give it.
No. No.
They see your points and
The first step, you feed the training data first into the compressor, and then you put the
training data could be itself.
yeah. But you don't know in advance where the data. If you did, you would need to.
Training data is supposed to be on the other side. It's not
Exactly.
Well, that might be different.
If the training and data are the same, basically, if you don't need to transmit it because the training data is there.
On the other hand, format like Broadly does silently ship training data.
Okay.
Broadly, one of the reasons Broadly is so good at source code and web fonts, and exactly at source code and web fonts, is that it ships with two dictionaries. One dictionary of HTML and JavaScript, basically, and CSS, I think, and one of web fonts. And it's hidden.
So
it's
it's
not part of the spec. There are a number of bytes used during the initialization. They are supposed to be set like this.
Yeah.
But these are actually two dictionaries.
Impressive. And it's shipped as
if
well.
you have Broadly on your computer, it contains two dictionaries.
Okay. It was okay. Yeah. So you have some kind of a preset dictionary when you want to decompress XML data or specific data. Yeah. Okay. But, so yeah, they have specific dictionaries. Yeah. Fantastic.
You showed that you have worked on this personal project for like 20 years. Do you have a secret of longevity for this project?
Well, secret is honor.
Do you have a recommendation for others who want to start a project?
Yeah, so the recommendation is go for it because it's basically stainless. You can use your code after years. It's almost boring because you have new version. You don't need to adapt to a new version of a compiler or whatever. It's you can do, instead of fixing these compiler things or compatibility things, you can start other projects or go ahead with.
Doing the same project for the next 20 years.
Yeah, exactly. Yeah.
What you didn't say though, there, you talked about source forge, but you've got this on GitHub as well.
Yes. because I've noticed, yeah, there's some fashion shifts to.
Slide, you mentioned SourceForge, but you shouldn't.
Yeah, it was on the history, but okay, I have some.
SourceForge.
If you go at the end of the hidden slides. Sorry, that's. Oh, no. Oh, here, yeah. Here. Oh, did I forget? I forget the GitHub. Oh, it's terrible. But you will find you Google GitHub zipAda and should be okay. Yeah.
Enough questions? Apparently. Yep.
It's.
So thanks again.
You're welcome.